Hi, everybody. Thank you for attending this session where we will be discussing what's new in Gloo Mesh and eBPF. My name is Gadban. I'm a field engineer here at solo.io, and this is a summary of what we'll be talking about today. So first, we'll set the stage, kind of talk about what eBPF actually is and what it can be useful for. We'll talk about Gloo Mesh and Istio and kind of where they fit into the picture. And then we'll start going into some specific topics related to that. So we'll talk about a little bit about Mesh and Istio networking. Then we'll talk about Kubernetes networking. And then we will focus on security and observability. So to get started, what actually is eBPF? So it's a Linux technology which enables users to run custom programs in the kernel, basically in their own sandbox. And eBPF itself stands for Extended Berkeley Packet Filter. And the reason it's called that is because it's kind of an extension or an evolution of classic BPF, the classic Berkeley Packet Filter, which you've probably used if you ever have used TCP dump. So when you use TCP dump to capture some network traffic, you can say things like, I want to capture all TCP traffic from this IP to this other IP. That is writing a packet filter, and that was implemented using classic BPF, which is where the name came from. Some of the pioneers of this technology have even said that eBPF at this point is no longer really an acronym. It's really a technology, and so it's kind of outgrown the acronym. And kind of to that point, eBPF and BPF, most of the time, at least in modern settings, can be used interchangeably. So at least on these slides and kind of going forward, if you see eBPF or BPF, they can be used interchangeably. Going back to the actual programs and technology, the programs that you write when you write an eBPF program, they're event-based programs, and they can be attached to various hook points in the kernel. And so that means that your program will essentially fire whenever an event that you've attached to will trigger your program to run. And so one example of that is something that's called a kprobe. So a kprobe program is something that's attached to a kernel function, and that can be attached to pretty much any kernel function. There are a few that it can't be, but for the most part, any kernel function can have a kprobe program attached to it. And then anytime that function is called, your program that's attached will actually be executed. And you'll be able to see things like the parameters or arguments that were used in calling of that kernel function. Another really important part about BPF is that the eBPF and BPF programs are verified to be safe. So when you load a program into the kernel, there is a verifier that will do things like check that it's guaranteed to return or doesn't have any infinite loops. It can only access specific sections of memory and things like that to basically give you a guarantee that the program is safe. And that's really important because when you're running programs in the kernel, you don't want to crash the kernel and basically render the system unusable. So with the verifier, you have a nice guarantee that if you're using a eBPF program in production, you won't bring down your system. So now let's talk about why you would want to use eBPF. One of the main use cases is networking. So remember that classic BPF, which kind of is the basis for eBPF, was built for efficiently filtering packets. So again, kind of the TCP dump example. And so because of the fact that it comes from that world, it's a natural fit to use eBPF to do various things in the networking kind of space. And one of the, kind of say it another way, basically what eBPF does, it allows for programmatic processing of packets at different locations. There are a lot of different locations in the Linux networking stack that you can attach an eBPF program to. And we'll kind of look at this in more depth. Another really good use case for eBPF is security. So since you're operating at the system level, at the kernel level, it's a really good fit. It's a really good place to do things like enforce security policies or even monitor sensitive operations because you're operating essentially at the kernel level. On top of that, since you can attach to various networking components, it's also a really good fit for doing things like network security because you can attach programs that can do advanced logic, and you can attach those to the various networking, the various pieces of networking functionality. And we'll look a little bit more at that as well. And then lastly is observability. So again, we've already talked a couple of times about attaching to kernel functions. Since you can attach to pretty much anything in the kernel, it's possible to extract data from that and get some really rich and low-level data and metrics. There are other hook points other than kind of the kprobe that we talked about. Another one, for example, is called the trace point. And a lot of that is kind of existed before eBPF came around, but eBPF, you can attach eBPF programs to these various hook points that are built for observability purposes, and they really give you a nice way of extracting some really low level and high fidelity data. So another important part is that eBPF is super efficient because it's operating inside of the kernel. And so that gives you the opportunity to process events as they happen in the kernel, which if you're operating in the user space is not really doable. So it kind of has unlocked a whole world of observability opportunities with eBPF. So now let's talk about Istio. So Istio is pretty popular service mesh at this point. It's a sidecar-based service mesh. It uses Envoy proxy as a data plane, and it builds on top of that. And really, if you're not familiar with service mesh, it's a technology that intends to solve several of the technical challenges that come with a microservices architecture. It's very widely used, very widely adopted. It's very widely used. It's used in production at tons of organizations and has a very large and active community. On the right here, you can see basically a sample architecture diagram that shows that you have your services deployed, and alongside that is a proxy that's deployed as a sidecar, which is where all of the data flows through. And then you have a control plane, which configures those proxies based on the state of the cluster, for example. So Gloo Mesh builds on top of that. Gloo Mesh is our service mesh platform. You can kind of think of it as an application networking platform that builds on top of Istio and kind of is intended to provide like a one-stop shop for your application networking concerns. So it handles your service mesh using Istio. We also can do API gateway functionality with Istio managed by Gloo Mesh. It also provides a management plane. So if you have more than one Istio installation, Gloo Mesh makes that easy to manage. And then on top of that, it provides kind of a higher level API that's more focused on use cases for operators or service owners and so on. Because the Istio API is relatively lower level. It ties pretty closely to the Envoy API, which is great. But we want to build on top of that to kind of focus on the use cases that an enterprise would need to use a service mesh for, rather than configuring the service mesh. You're configuring your use cases, and then under the scenes, Istio or whatever needs to be is configured to actually enforce or express kind of what you've configured with our API. So let's go ahead and dig into mesh networking, specifically Istio. We've already kind of seen in the previous diagram how this Istio sidecar proxies, which are Envoy, kind of live alongside your application. And so those network proxies handle all of the traffic that's flowing to and from the application container. And the traffic that's intended to either go to the application container or leave the application container is transparently redirected to that proxy. And that redirection occurs with IP tables rules. Kind of the standard way of doing that is that when every pod starts up, when the proxy is injected to that pod, there's an init container that runs that will create some IP tables rules on the given node that it's running on to handle that redirection. And so anything that's really intended for the pod, the main container in that pod, will be redirected to the Envoy proxy, and the same would apply for outbound traffic as well. So the traffic would get redirected to the proxy. The proxy actually does its magic where it can, enforce whatever policies are in place. It can process it and maybe you want to do like retries, or you want to do some advanced load balancing, or whatever it is that you're using the service mesh for. Envoy will take care of that, and then it will also forward to the right destination. So going back to how that redirection actually happens, this is a really great diagram, and there's a link at the bottom if you're interested in kind of seeing the blog article it came from. But this is achieved using IP tables, and it's somewhat complicated to get this working. So there's a lot of, I don't want to call it magic, but there's a lot of IP tables configuration that happens to handle all of the inbound and outbound redirection. And so this diagram kind of goes into depth of all of the different places where IP tables is making, the IP tables rules are being used to determine, okay, this packet actually needs to be redirected to go to Envoy, and there's a specific port that Envoy is listening on, for example, for the inbound traffic to the application container. And there's also a specific port for outbound traffic from the application container. And those IP tables rules are kind of controlling to make sure the packets go where they need to go. So it works great. It is just a little confusing if you're not familiar with what's going on. So if you want to look at that kind of like zoomed out, what happens is, you have your pet store application in this case, and you have your Istio proxy. So if some traffic were to leave the pet store app, maybe talking to another service, it would use a socket and it would send out a packet. And then what would happen is the network stack here, which has everything in the Linux kernel that's related to networking, the IP tables rule would come into play, and that packet would be redirected to this socket here on the Envoy proxy. But then you have other IP tables rules that say, okay, this is intended for this destination, really that needs to go to the Envoy proxy. And so you're kind of traversing through the network stack on both cases to get to where you correctly need to be. So as I mentioned, it works well. It's battle tested. Istio is running in production and has been for years now. But there can be concerns that the sidecar injection model and traffic redirection model, you are doing that network traversal in the kernel for pretty much you're doing that twice for every flow. And so there are ways that we can improve that. And that's one of the places that eBPF can help. So Istio data path acceleration is a way of accomplishing that. So again, you can attach a eBPF program to pretty much anywhere in the network stack. There are very specific places, but there's a network location for a eBPF program, like for example, a network socket. So when those network sockets that we were looking at for the pet store and for the Envoy container, you can attach a eBPF program to those sockets. And then there is another kind of, so there's a special kind of BPF map, which essentially is saying for this socket, anytime that a request or packet is flowing to one socket, I actually want to redirect that directly to another socket. So you're kind of keeping a map of from this socket to this socket. And when you do that, you can skip all of the rest of the traversal that we were looking at. So you can point directly to where you need to go. So what that kind of looks like is, again, we have this application, the pet store, and we have our Istio proxy. We have the sockets used for communication. So in this example, right, Istio proxy is receiving communication from the pet store because the pet store is sending out packets. And so for these sockets, what we can do is we can have Gloo Mesh help and attach an eBPF program to each one of those sockets. And then what happens is, since we're keeping a map, and we can do this programmatically, so we can say, okay, in a given pod, this is the application container, this is the Envoy proxy, the sidecar proxy. What I want to do is that whenever a packet is sent to this socket, the real destination is this socket over here for Envoy. And that happens by the programmatically, we can keep that map up to date, and we can skip all of the IP tables magic that needed to happen to make that happen. So we'll be able to do that with Gloo Mesh. We're doing things like benchmarking and confirming that it's ready for production, et cetera. We have seen improvements to throughput and latency. So there's more to come on that. There is a caveat here. I'm linking to a blog article that we published. At Solo, we don't think that Envoy is going anywhere. This functionality is really about shortening the path, basically, to go from application container to the sidecar, but we still think that Envoy as a sidecar is here to stay. So if you're interested in that, I highly recommend checking out this blog. Okay, so let's talk quickly about Kubernetes networking. So Kubernetes networking, what we're gonna do is we'll take a kind of a, this is kind of foundational for some of the other topics. So Kubernetes networking itself, it relies on an underlying network plugin to implement cluster networking. And cluster networking is, for example, the pod-to-pod communication. There are some specific rules that you need to follow to actually implement Kubernetes networking. And for example, one of those is that pods can talk to other pods, and pods have their own IP address. The networking is implemented typically as what's called a CNI plugin, and CNI is a container network interface. We'll talk more about that. But the CNI itself it's a spec that that defines functionality for example, create a network interface that's called ETH0 in a specific container, right? And another really interesting thing about the CNI spec is that it allows for chaining. So you can have a chain of CNI plugins. So like we just said, the example is create network interface ETH0 in container bar. So every plugin will get to operate at that time. So if we're doing the creation of the network interface, one of the CNI plugins will operate on it and maybe it creates the interface. Then the next plugin will be able to modify that interface or add some additional functionality. You can kind of think of it as like composition of different networking features. And then lastly, I call out that the container runtime interface, or the CRI, is what actually delegates the control to the CNI. So the CRI is responsible for doing things like creating the containers or creating like the Linux namespaces that define a pod boundary. But when it gets to actually creating, for example, the network interfaces that your containers would use, that is the job of the CNI, and the CRI delegates that to the CNI. So kind of seeing that in action, we have a node here, a Kubernetes node. It has some network interface that allows the actual node to make network requests, but we also have the kubelet and then the CRI and the CNI. And so when we have to do something like create a pod, so the kubelet is trying to create this pod that's named bar. What it will do is delegate to the CRI to actually create the containers, create the pod boundary, whatever it needs to do. So in this case, we have one container. We'll create that container, the CRI plugin will. And then the CNI gets called, and that is where the networking interfaces in that container get created. So now the CNI plugin is going to actually create, for example, an ETH0 interface that's available to this bar container, and it's kind of in the network namespace of this bar pod. And then again, with chain plugins, during that step where we're, for example, creating this ETH0 interface, all of the plugins in the chain get to do some work. They get to operate, for example, on the interface. And then once that's done, we have the pod created, we have the container created, we have the networking interface created, and now the pod and the application container inside of the pod can operate as usual, as normal, right? So to the applications container, it's making a network request, maybe it's calling another pod in the cluster, and basically the routing is set up to where that request can leave and then traffic can come back. So this is kind of a zoomed out view. Basically, if we have, let's say we have 3 pods, we have a pet store, a foo, and a bar pod. The foo and the bar pod can talk to pet store, and they're kind of going out their own network interface. And then on the pet store side, the server side, it's going to the pet store application, and it's going through the network interface on the pet store side. So with that kind of as a basis, let's talk about security. So first, we'll talk about security in Istio. Istio has a very powerful set of features related to security. Kind of one of the core concepts in Istio security, though, is the concept of a service identity. And that means that basically is how each workload instance in the service mesh has a cryptographically verified identity. And that's done using X509 certificates. It also is done based on the service account of the pod that's running. So when you have a workload that has, for example, in this diagram over here, we have service A, we have a sidecar proxy, and the service account that's running this pod is what is used as the basis for the Istio identity. And then the way that this works is that the Istio agent, which is another process running in that pod, will submit a CSR or certificate signing request to the control plane. And depending on what CA or certificate authority the control plane is set up to use, that CA will then sign the CSR, and that is then results in a signed certificate, and then the private key is available to the proxy. And that's kind of the basis for the identity. So when this proxy makes a network request for the service A, the identity is known in this proxy. And so mutual TLS is a really important feature in Istio. It's kind of enabled out of the box. But when we're using mutual TLS, since every workload will have an identity, that means that for every request, basically, as long as it's using mutual TLS, you will have a client side and a server side well-known identity that's cryptographically secure. So kind of just to solidify that, say we have a deployment, which is the pet store deployment. It's running in the default namespace. and it uses a service account named pet store. So here's the service account. The end result of that CSR kind of flow, the provision certificate flow, is we get a certificate and key that correspond to this identity. Cluster.local is a trust domain. We won't go into details in this talk about that, but really it just identifies the mesh more or less that is a part of. So in this example, the identity would be cluster.local/ns/default for default namespace, and then /sa/pet store for the pet store service account. So authentication, we already kind of touched on. It's all based on those certificates that are provisioned automatically for you. Automatically out of the box, you're going to get mutual TLS between all workloads that have a sidecar. And it is permissive by default, which means that Istio proxies will accept requests from both other Istio proxies, which will be done over mutual TLS, but it will also accept plain text requests. So you kind of can think of that as like a legacy client that hasn't been onboarded to the mesh yet. But you can change that to strict, which means it will only accept mutual TLS properly authenticated requests. Authorization is built on top of that, where authorization allows you to do, there's essentially an authorization engine that runs in the Envoy proxy, in the Istio proxy. And when you're using mutual TLS, since you have the client-side identity, you can also write authorization rules based on the identity of the service talking to you. And then on top of that, since Envoy works at layer 7, you have access to all of the HTTP request attributes. So the end result is that this example here on the right gives you a authorization policy that will say that for the pet store application, I will accept requests from the cluster.local default foo identity from that client. I will accept requests that are gets to /bar. And so this is a really powerful feature that allows you to write really complex authorization rules. And again, that's all enforced in proxy. You can kind of do that. You basically get it for free when you use Istio. So Gloo Mesh kind of, again, builds on top of that by providing a single API called the access policy that controls both the authorization and authentication configs, and that it also can do that on a multi-cluster level. So when you define an access policy, you'll define, in this example, we only have authorization, but we're doing it based on the service account, just like the Istio identity is based on. And then this can be applied to, say, multiple clusters in your mesh. So to kind of look at what actually happens, when we create an access policy in Gloo Mesh, that is then translated into the actual Istio primitives that would enforce that, basically the desire or the intent of this access policy. So that's great. And like I mentioned, it's a really powerful set of features. It's one of the main reasons that Istio has become so popular, in my opinion. But there are a few gaps in what Istio provides as a security mechanism. All of it relies on sidecars being present. So if the sidecar can be circumvented, if the sidecar proxy can be circumvented, it can't enforce any of the security features. And then also only TCP traffic is routed through the proxy. So anything UDP based kind of is not part of this flow. So ultimately, Istio is not a network firewall, and it never was intended to be. So even the Istio best practices security documentation calls out that, to further secure your mesh, it's probably worth, basically exercising defense in depth. And you can do so, for example, using a network policy. So a network policy is a Kubernetes API that is essentially defining what you would think of as a firewall rule, a network traffic firewall rule, because it operates at layers 3 and 4 IP address and port level. And it's typically implemented by your cluster network plugin. The identity for this policy is based on the namespace or pod labels that you want to either allow or deny traffic to. So in this example here on the right, we're saying that for pet store application, I'm going to accept traffic from a pod that has a label of access is true. And so what that would look like is going back to our kind of 3 pod setup, we have foo, bar, and pet store. Foo has a label of access true, and bar has a label of access false. So as you would expect, the foo pod can talk to pet store, but the bar pod cannot. And again, this is done using labels on the pod, which is a little different than we were talking about with Istio, which is the service account identity. So with Gloo Mesh, and this is something else that we think eBPF can help us with, we want to be able to provide defense in depth out of the box. And so we want to use our already unified API, the access policy, to be able to help with the network level security using eBPF. And we want to be able to do that regardless of the underlying CNI that you're using. And that will give you kind of a consistent identity from the mesh to the network level. And we'll be able to do that without relying on proxies, because for the network level, we can do that with eBPF. And so what that kind of would look like is we can have a Gloo Mesh CNI plugin. So again, in the chain of plugins, right, each plugin gets an opportunity to act. And in our case, the Gloo Mesh CNI plugin can add some functionality. And so when that interface is being created for a given container, we can attach an eBPF program that can, that can be programmed, and it has smarts to be able to do things like enforce security at this interface. And so what we can then do is, based on our access policy API, when you're talking about network security, we can do things like this example is allowing to the pet store only a pod that has a service account that is essentially labeled with account foo. Then that client is allowed to talk to pet store, but anything else is not. And so what that means is that the foo pod, which is running with a service account of foo, that's allowed at the network level, and it's also allowed at the Istio or service mesh level, but the bar pod is not. And so we can achieve what some folks call microsegmentation. We can do that based on the service account identity, which is consistent with the service mesh, and we can have a single API that controls all of that. Okay, so lastly, let's talk about observability. As I mentioned, observability, there's a lot of power there with eBPF, but to get to that point, let's kind of talk about what exists today. So Envoy Proxy has a really fantastic set of statistics and metrics that it gathers for downstream and upstream traffic. So basically, as traffic flows through the proxy, there's a lot of statistics that are being generated for that traffic. And that's at the connection level, the request level, and there's a lot more to it than that. But you're getting a lot of data when you're using Envoy. The stats that are in Envoy can be exported as Prometheus metrics, which is becoming pretty much the de facto standard of kind of standard Kubernetes style monitoring. On top of that, Istio has its own metrics that are generated in proxy, and that kind of provides service level style metrics. So you can think of like what client is talking to what service. You can get metrics for that from Istio, and those are exported by Prometheus metrics by default. And so when you combine the Envoy metrics as well as the Istio metrics, you get a really rich set of data to help monitor and understand your mesh. So this is just an example of kind of like, this is the Istio dashboard, and you can see that this is specifically for a service that's the detail service. And you can see in this screenshot, the different types of data you get. You can think of it as like kind of the golden signals that's intended to be supplied out of the box when you're using Istio and Envoy metrics. So on top of that, Gloo Mesh, again, kind of builds on top of it. And what Gloo Mesh can do, since you have that management plane, it can help with the aggregation of the metrics and statistics for all of the meshes that make up your virtual mesh, or whatever you want to think of as the various components that make up your mesh. Gloo Mesh can help with the aggregation of that. And then on top of that, since it's aggregating from different clusters, we can augment that data with cluster level data. So you can know which metric is coming from which cluster. And then the end result of that is we can do things like our service graph, which allows you to do, basically track your service flow, your network graph, but it also is cluster aware. So in this example, right, we have cluster 1 and cluster 2. And so you can see the traffic flowing across both of the clusters in this mesh. That being said, there's a lot of data there, but there are a few gaps. So again, kind of as we talked about in security, it all relies on the proxy being there. So if you have workloads that say have not been onboarded to the mesh, you don't have any of this data because you don't have a proxy living alongside the application. You also are limited to what Envoy and Istio gather as far as metrics go. So as I was saying, there's a bunch of data there, but one example of where it might fall short is that Envoy by default captures to the endpoint level. So if you have a service that's usually made up of different pods, right, different replicas, that's considered an endpoint. And there's a lot of really good endpoint level statistics in Envoy, but because of the cardinality concerns when you're using Prometheus, that is not exported by default or even exported at all for Prometheus style metrics. So if you need very low level endpoint per endpoint level data, you can't get that through Prometheus metrics with Envoy. And then additionally, you may have environmental issues that are kind of even lower level than Envoy, right? They may be node level or so on, and you can't get that through Envoy or Istio. So this is where eBPF can help out. eBPF is a natural fit for tracing observability for several of the reasons that we talked about already. I do have a link here to Performance Analysis Superpowers with Linux eBPF by Brendan Gregg. It's a fantastic talk. I recommend you check it out. It goes into way more detail than I can here. But really, since eBPF is working at the kernel level, you can get a ton of low-level data on pretty much anything that's happening on your system. And that is done at the kernel. So you don't need a proxy. You don't need, you don't need to have a sidecar running. You can get that directly from the kernel. And so it's a really nice fit for kind of getting data from, from workloads that don't have a proxy, or if you do have a proxy and you need some specific custom data, you can use eBPF to do that as well. And so when you combine Istio and Envoy and eBPF powered observability, you get a really, really powerful set of observability data. So to kind of look at that, again, in this example, we have the 3 pods. In this case, they're running on 2 different nodes, and only the pet store in this example has the Istio proxy injected. Only this is the part of the service mesh. The foo and the bar pods are not. They haven't been onboarded yet. And so when we're using a Prometheus instance to scrape some data, from the pet store app, we can go ahead and get the app data. We can go ahead and get Istio and Envoy metrics. So we have a pretty good set of information that we need from this workload. But then the foo and bar pods, we can only get application level metrics. So is that enough data for troubleshooting? Maybe eBPF can help to get a richer set of data, a richer set of metrics from these applications. So what we can do is using Gloo Mesh, and then we also have another open source project. We have a talk at SoloCon as well on Bumblebee. Really, what that's intending to do is provide a nice workflow for observability-based eBPF programs, and it makes it to where you can deploy those programs from any OCI registry. So Gloo Mesh can utilize that kind of functionality, and what we can do is say we have an eBPF program that can get some network level statistics from the node, regardless if you have an Istio proxy or not. Gloo Mesh can kind of pull that program as an OCI image from your registry, where you're storing your other container images. It can deploy that to the nodes in the cluster, and then now we can scrape the Istio proxy for the pet store, which is injected with Istio proxy, so we can get the app Istio and Envoy metrics from pet store. We can get the app metrics from foo and bar, which don't have Istio proxy. And then we can scrape the eBPF programs to get the really low level metrics that, for example, for foo and bar, they don't have any network statistics. We can get those from the node from our eBPF program. And then we can also get some custom metrics. Maybe we need some higher fidelity data about the pet store. We can get that from the eBPF program running on that node. And so you get kind of this like best of both worlds where you can get low level eBPF style observability data, as well as the typical application level data. Okay, so to summarize, eBPF is a very exciting technology. It unlocks a lot of really cool stuff that hasn't really been possible. It also allows us to improve a lot of things. And Gloo Mesh intends to be able to leverage eBPF and do so in a way that you can adopt it, you can adopt with what you need without having to rely on specific implementations. Gloo Mesh can help kind of manage that as you need it. Also, with the speed that this area is changing, if any of this sounds interesting to you, please let us know. Let us know what you think. And that's all I have. Thank you very much.